Hi everyone, my name is Xuanwei Feng. My topic is PMTUD is not Panacea, revisiting AP fragmentation attacks against TCP. The work of this paper is cooperated by researchers from Tsinghua University, George Mason University, Qianxin Group, and University of California, Riverside. In this paper, we study on the complex interactions between AP fragmentation and TCP. And we demonstrate that AP fragmentation can be abused to poison TCP traffic, even if the originators performs PMTUD discovery to avoid AP fragmentation. I will introduce our work as the following 5 steps. First, I will introduce the widely deployed mechanism of PMTUD discovery, that is PMTUD. As an Internet Protocol mechanism, AP fragmentation is designed to split large packets into multiple smaller fragments for them to pass through a network that enforces a smaller MTU, thus avoiding packets discarded by the network. When the fragments arrive at the destination, they are reassembled into the original packets. AP fragmentation has been widely abused by attackers to evade intrusion detection systems and launch DOS attacks. Besides, attackers can misuse AP fragmentation to attack UDP-based applications and services, for example, poisoning DNS cache. However, it is a widespread belief that TCP is not vulnerable to AP fragmentation attacks. Since TCP performs the path maximum transmission unit discovery mechanism by default, which can avoid AP fragmentation by dynamically matching the maximum size of TCP segments with the MTU of the path from the server to the client. After a TCP connection is established, the server first generates TCP segments based on the initialized MSS value, for example, 1460 octets in Ethernet, and sets the don't fragment flag in IP header as true. During being forwarded, if the packet size exceeds the next hop MTU of an intermediate router, the router will discard the packet and issue an ICMP fragmentation needed message to the server. According to PMTUD specifications, the issued ICMP message usually carries the router's next hop MTU value, that is LMTU by default. After the server receives the ICMP message and confirms that LMTU is greater than its acceptable minimum PMTU value, the server will resize the MSS value of subsequent TCP segments according to the router's next hop MTU value. Besides, the server sets the don't fragment flag of the packets as true before sending them out. The server repeats this process until a packet with certain size can be forwarded to the client successfully, and this MTU size will be set as PMTU value and maintained at the IP layer. This mode can effectively avoid AP fragmentation on TCP segments and has been widely adopted on almost all major OSs, operating systems. However, we discovered 2 situations under which AP fragmentation can still be triggered on TCP segments, even if the server performs PMTUD. First, when the next hop MTU of an intermediate router is smaller than the server's acceptable minimum path MTU value, TCP segments from the server will be fragmented by the router. During the packet being forwarded, if the packet size exceeds the next hop MTU of a router, the router will discard the packet and issue an ICMP fragmentation needed message to the server. Particularly, the router's next hop MTU value, that is LMTU, is less than the server's acceptable minimum path MTU value, that is, min PMTU. Under this situation, the server will resize the NDSS of subsequent TCP segments according to its acceptable minimum path MTU value, instead of the router's next hop MTU value. Besides, the server will also clear the don't fragment flag of the packets. Thus, the packets are allowed to be fragmented by the intermediate router, which means if one router's next hop MTU value is less than the server's acceptable minimum path MTU value, IP fragmentation on TCP will occur at routers, although the server may enable path MTU discovery mechanism. In RFC 1191, the acceptable minimum path MTU value of hosts is set as 576 octets. However, we observe that the detailed implementations may adopt different values in the real world. For example, 256 in FreeBSD, 296 in macOS, 552 in Linux, and 596 in Windows. Second, when the server's path MTU values between the IP layer and the TCP layer are desynchronized due to a maliciously crafted ICMP error message, the server could be tricked into fragmenting TCP segments. As shown in this figure, when an ICMP message is not triggered by the TCP connection, even if the server receives the ICMP error message, it will not notify its TCP layer to resize the MSS of subsequent segments due to the lack of TCP-related information such as source port, destination port, or sequence numbers. The IP layer of the server defers the feedback of the updated PMTU until it receives the segments from TCP and preserves the presence of the TCP connection passively. The deferred response results in the desynchronization on the path MTU value between the IP layer and the TCP layer for a short period of time, causing TCP to write oversized segments to IP. Thereafter, IP will fragment those oversized TCP segments using its acceptable minimum PMTU value and set the DF flag of the fragments as false. This vulnerability presents in Linux kernel version 3.8.1 and beyond. This figure shows the crafted ICMP fragmentation needed message issued by the attacker. The message is embedded with an ICMP echo reply packet, and by simply pending X to meet the last requirement, the attacker can evade the checks from both RFC 792 and RFC 1812 to trick the server into fragmenting its TCP segments. To sum up, since the received ICMP error messages may vary greatly, servers with different OS implementations handle them in different ways for performance considerations or for exception handling, rather than just decreasing the MSS of TCP segments. However, the two special handling modes incur undesired IP fragmentation on TCP. Once IP fragmentation on TCP could be triggered, attackers can inject forged fragments into the victim connection to poison the target TCP traffic without guessing the sequence and acknowledgement numbers that are always carried in the first benign fragment. In order to poison the target TCP traffic, the attacker needs to perform three main steps, that is, infer the presence of a victim TCP connection between the server and the client, triggering IP fragmentation on the server's TCP segments by exploiting the two IP fragmentation situations and impersonating the victim server and forge malicious fragments to the victim client. In the first step, for different cases, the attacker infers the presence of the victim TCP connection by using two classical approaches. For example, by using applications when posing HTTP traffic, or by using TCP IP side channels when posing BGP traffic. In the second step, the attacker triggers IP fragmentation on the server's TCP segments by detecting IP fragmentation at routers or by forcing IP fragmentation at vulnerable servers than we detailed previously. In the third step, the attacker impersonates the victim server and forwards malicious fragments to the victim client. These forged fragments will be cached in the client. Finally, the victim client will misresemble binary fragments and the forged fragments that carry correct IPID value together. Once the checksum of TCP can be evaded, the original TCP segment will be poisoned. Our case studies on both HTTP and BGP demonstrate the feasibility and effectiveness of posing TCP-based applications via IP fragmentation. For example, an attacker may poison web cache or intercept HTTP redirections by performing our attack. We propose two countermeasures to prevent the identified attacks while addressing the root causes. First, we propose to avoid IP fragmentation at intermediate routers. It's difficult to remove or fix all those routers from the internet in the near future. Hence, one solution is to enhance the server's accepted minimal path MTU value between being less than the intermediate router's next hop MTU value. As a result, the server will adjust the MSS of its TCP segments according to the router's next hop MTU value to avoid IP fragmentation. Second, we propose to avoid IP fragmentation at servers. We can fix the identified vulnerability by using two solutions. First, when an ICMP message embedded with a packet that does not perform PMTUD arrives, one solution for the server is to discard the received message directly. Since correct packets originated from protocols that do not perform PMTUD will not trigger ICMP fragmentation needed messages at all. Second, if attackers forge ICMP fragmentation needed messages embedded with protocol data that performs PMTUD, it is still challenging for the server to judge the legitimacy of the message. As a result, when such a message is received, the IP layer should actively update the MTU information carried in the message to the TCP layer. Thus, the TCP layer can achieve a strict synchronization on the path MTU value with the IP level to avoid IP fragmentation. Conclusion. In this paper, we uncover two situations under which IP fragmentation can be triggered on TCP, and we demonstrate the feasibility and effectiveness of posing TCP-based applications via IP fragmentation. Finally, we propose two countermeasures to prevent the identified attacks. Thanks for listening.